A host device generates a data packet with a known destination IP address, ready for transmission. But instead, the packet hits a barrier and scatters. The transmission fails because an IP address alone is useless on a local wire. Without a Layer 2 destination address, the packet cannot be placed into a frame. Every device on an Ethernet LAN operates with two concurrent identities, shown here. On the right, the logical IP address handles end-to-end routing across remote networks. On the left, the physical MAC address is valid only on the local segment, required for NIC-to-NIC communication. To encapsulate an IP packet into an Ethernet frame, the sending hardware must have the receiving hardware's exact MAC address. Manually mapping these addresses across an enterprise network would be an impossible, error-prone task. Networks therefore rely on an automated mechanism to map Layer 3 addresses to Layer 2 hardware identifiers. On an IPv4 network, this is the Address Resolution Protocol, or ARP. Before sending any traffic, a host first checks its own RAM for an existing mapping. This temporary ledger is the ARP table. It stores the known relationships between IPv4 addresses and their corresponding MAC addresses. If the destination IP is not already in this table, the host pauses transmission to generate an ARP request. The request includes the sender's details and the target's IP, but because the target MAC is unknown, it uses the all-F broadcast MAC address. This broadcast destination forces the local switch to flood the frame out of every connected port on the segment. Every device on that segment receives the broadcast, which requires a small amount of local processing power. Each receiving device checks the target IP. If it doesn't match their own, they drop the frame. Only the device with the exact matching IPv4 address continues the process. That host generates an ARP reply containing its MAC address and sends it as a unicast frame directly back to the requester. The requester then adds this mapping to its ARP table. This demonstrates how local delivery is entirely dependent on resolving these unauthenticated broadcast queries. This process has a limit. Routers do not forward broadcast traffic. This means an ARP request cannot leave the local network. A host uses its subnet mask to determine if a destination IP is local or remote before it even checks the ARP table. If the destination is on a remote network, the host resolves the MAC address of its default gateway instead of the final destination. Here, a PC sends data to a server across a wide area link involving multiple routers. In the first hop, PC1 targets the final IP address at Layer 3, but targets Router 1's MAC address at Layer 2. When Router 1 receives the frame, it strips off the Ethernet header to examine the underlying IP packet. After checking its routing table, the router determines where to send the packet next and prepares a new Layer 2 frame. For the second hop, Router 1 encapsulates the original IP packet in a new frame using Router 2's MAC address as the new destination. Inside that frame, the source and destination IP addresses remain unchanged throughout the entire journey. Router 2 repeats this de-encapsulation and then uses ARP on the final network to find the MAC address of the target server. This illustrates how packet delivery works. End-to-end IP addresses stay constant, but Layer 2 MAC addresses are rewritten at every router boundary along the path. There is a trade-off in the original ARP design. It operates on absolute trust. When an ARP reply arrives, a host assumes it is legitimate and updates its table without verifying the sender. A threat actor can exploit this through ARP spoofing. The attacker sends a fake ARP reply, claiming their own MAC address is the correct mapping for the default gateway's IP. The victim updates its ARP cache with this malicious mapping, unknowingly routing its outbound traffic to the attacker. This can lead to sensitive data being intercepted, manipulated in transit, or blocked entirely. Because IPv4 relies on these unauthenticated broadcasts, it creates a persistent security risk, a vulnerability addressed by the more targeted communication methods found in IPv6. While functional, ARP's reliance on unauthenticated broadcasts creates limitations in security and network efficiency. In IPv6 networks, this is replaced by the Neighbor Discovery Protocol, or ND. IPv6 eliminates network-wide broadcasts entirely. Instead, ND uses ICMP-v6 messages, neighbor solicitation, and neighbor advertisement to perform address resolution. Rather than shouting to every device, ND sends its request to a specialized, targeted multicast address. Because this address is derived from the target's IP, only the intended recipient's network interface pays attention to the message. Every other device on the network can filter the query at the hardware level, saving CPU resources across the entire segment. Neighbor Discovery also manages router discovery and auto-configuration, serving as a comprehensive upgrade over the legacy ARP process. Whether it's the broadcast method of IPv4 or the targeted multicast of IPv6, address resolution allows software-defined addresses to function on physical network hardware.